All right, let's get right to it. What you're looking at here is gas metal arc welding, or GMAW. This process is quite literally what holds our modern world together, from cars to bridges to skyscrapers. But to get a strong, sound weld, every single piece of this equipment has to work in perfect harmony. So let's pull back the curtain and see how each component really works.
Okay, so this is the whole system laid out. You can think of it as a three-part harmony. You've got electricity, you've got a consumable wire, and you've got a shielding gas. Each one plays a critical role, and they all have to converge perfectly right there at the welding arc. We're going to trace the path of each one, from its source all the way to the weld itself. First up, let's follow the power. We're going to trace the path of the electrical current, and that journey, of course, begins at the power source. This right here is the command center. This is where the welder is going to set two absolutely crucial parameters: voltage, which is kind of like electrical pressure, and the wire feed speed. Now, GMAW power sources are smart. They're what we call constant voltage, which means the machine works hard to keep the voltage steady while the amperage automatically adjusts to perfectly melt the wire as it's being fed. That's the real secret to getting a stable, consistent arc. You know, in welding, electricity is pretty much a one-way street. We almost always use what's called direct current electrode positive, or DCE. All that means is we make the wire positive and the piece we're welding negative. By setting it up this way, we get a really smooth, stable arc and the super efficient transfer of metal from the wire to the workpiece. For most jobs, it's just the way to go. Now, not all power sources are built the same. A thyristor-based machine, for instance, gives you this incredibly fine-tuned control. You can adjust the settings with a knob, even while you're welding, which makes it perfect for automated or robotic setups. On the other hand, you have the tapped transformer machines. They're simpler, more old school, with fixed settings you choose with a switch. Less flexible for sure, but also very straightforward to operate. Ever see a percentage like this on a welder and wonder what it means? That's the duty cycle. Think of it like a sprinter. It means this machine can run at its full rated power for 6 minutes straight, but then it absolutely has to rest for 4 minutes to cool down. Knowing this number is critical. It tells you the machine's limits. So, what if you need to weld nonstop, say in a robotic application? Well, you can't just redline the machine continuously. You'll cook it. Instead, you have to do the math and dial back the current to a safe level for 100% duty cycle. For this 350 amp machine, that means you can't push it past about 270 amps if you want it to run all day without overheating. Long welding cables, they're a classic headache in any big fab shop. The farther that electricity has to travel, the more voltage you lose along the way. So that 20 volts you carefully set on the machine, by the time it gets to the torch 50 feet away, it might be down to 18 volts. And that 2-volt drop is more than enough to destabilize your arc and ruin the weld. The solution is simple. Either use thicker cables, or you have to crank up the voltage at the source to compensate for that drop. Okay, so that covers the electricity side of things. Now let's switch gears and talk about the wire. This is our consumable, our filler metal, and its journey from that big spool to the arc is just as critical. The wire feed system really has one simple job: deliver that wire to the weld pool smoothly and at a perfectly consistent speed. It goes from the spool, gets pulled by the feeder, and then gets pushed by these rollers all the way to the torch. Any little snag or hiccup in this delivery system, and you're going to see it in the final weld. Guaranteed. And here's a closer look at the heart of the system, the feed rollers. The details here are everything. The little groove in the roller has to be a perfect match for the diameter of your wire, and the pressure you apply is a delicate balance. Too loose, the wire slips. Too tight, and you'll crush the wire, which can cause a nasty jam down the line. Trust me, I've seen it 1,000 times. And when you get that wire feed just right, this is the beautiful result. You get a super stable arc. You can see how consistent it is on that chart to the left, and that translates directly into a perfect, smooth weld bead like the one on the right. It's just a fantastic thing to see when the mechanics and the electronics are all working in perfect sync. All right, last but certainly not least, let's talk about our shielding gas. I want you to think of this gas as a force field, an invisible bubble that we create around the molten weld to protect it from the outside air. Without this protection, your weld is absolutely doomed from the start. So, the gas starts its life in a high-pressure cylinder, but this little setup right here, the regulator and flow meter, tames it. It knocks the pressure way down to a safe, usable level and lets you precisely dial in the flow rate you need, usually somewhere between 15 and 30 liters per minute. A common mistake is getting this setting wrong. Too little gas and you don't get protection, too much and you just create turbulence that also ruins the shield. And that gas shield, man, is it fragile? Just look at this data. It's pretty stark. A little breeze, something you'd barely even notice, is enough to completely blow that shield away. Once that happens, the weld gets contaminated and you get porosity, these tiny little bubbles or blowholes. That's exactly why you always see welders setting up screens when they're working outside. It's not for show, it's an essential precaution.
But wind isn't your only enemy. Spatter buildup inside the nozzle can be just as damaging. See all those little balls of metal? They obstruct the gas flow and create turbulence. And before you know it, that turbulence has destroyed your perfect, smooth gas shield. A clean nozzle is a happy nozzle, and keeping it clean is a non-negotiable part of good welding. Okay, we've followed the electricity, we followed the wire, and we followed the gas. They're all racing to the same point. Now it's time for the main event. What actually happens at the welding arc itself? This is where it all comes together. Believe it or not, the shielding gas you choose has a massive impact on how the metal gets from the wire to the workpiece. If you're using a gas rich in CO2, you often get what's called globular transfer. Think of it as big, clumsy drops of metal falling into the weld. It works, but it's messy and creates a lot of spatter. But switch to an argon-rich gas, and you can achieve a beautiful spray transfer, a fine mist of tiny droplets that are literally projected across the arc. The result is a much cleaner, smoother weld. Now, for thinner materials where you can't just blast it with heat, we use a completely different method called short-circuiting transfer. The wire actually taps the weld pool, creating a short circuit that causes a surge of current that melts the tip of the wire like a fuse blowing. This whole cycle repeats over 50 times every single second. It's a much cooler process, which is perfect for delicate work where you don't want to burn through the metal. So the bottom line is pretty clear. You've got to use the right tool for the right job. Globular and spray are your heavy hitters for thick plate. Short-circuiting is for finesse work on thinner stuff, and there's another one called pulse transfer, which is kind of the jack of all trades, giving you spray-like quality but with less heat. Knowing which one to pick, well, that's what separates a good welder from a great one. And this right here is exactly why that shielding gas is so unbelievably critical. The normal air that we're breathing right now is pure poison to molten steel. Any failure in your gas delivery system, a leak in the hose, a clogged nozzle, a gust of wind, and you're letting that poison right into your weld.
The difference is truly night and day. On the left, you've got a sound, strong weld. On the right, you have a disaster waiting to happen. Those little cracks and holes aren't just ugly. They are serious defects, ticking time bombs that can compromise the integrity of the entire structure and lead to catastrophic failure down the line.
So there you have it. The intricate dance of electricity, wire, and gas that has to be perfectly choreographed to create a sound weld. Every single component, from the cylinder to the nozzle, has a vital role to play, and a failure in any one part can ruin the whole performance. So the next time you see a bad weld, ask yourself this question: where did the system break down? Because in the world of welding, the devil is always, always in the details.